keep talking about this longest element of the Coxeter. We showed last time that any finite Coxeter group has a unique longest element. Well, a unique maximum element is bigger than everything else in the Bruhat order. And we call it W naught. Okay? And last time we were talking about some properties of this very nice element W naught. So the first property is that the square is the identity. By the way, here's a question that you might have been asking yourself. You know that all reflections square are the identity, and so there's a very natural question, which is whether W naught is a reflection or not. So let's put that over here, and I'll post it as a question on the forum. So you should think about that. The other thing we showed is that the length of W naught is equal to the length of W naught minus the length of W. So if you're in floor K of the Bruhat order, and if you multiply by W naught, then you end up in top floor minus K. Now, the third property, let me write it down, and then we'll parse what this means. So remember what this set T sub L is. We talked about this set earlier. We said that it was the set of reflections that made W shorter. So reflections T such that they make W shorter. And we said that this was a good set because one thing we showed is that the length of the word, the length of an element, is equal to the number of reflections in this set. So what is this statement saying? This statement is saying that the reflections that shorten W naught are precisely the ones that do not shorten W. The last property that I would like to show is that the length of W naught, the maximum length of the poset, is equal to the number of reflections in the group. Okay. So I'll remind you that last time we proved this, and now I'm going to prove 3 and 4. So well, maybe 4 is shorter, so we're going to do 4 here, and we're going to do 3 here. So proof of 3. It's not too bad, actually. What does it mean for T to be in the set? It means that when you multiply W naught by T, it becomes shorter. Now, remember that always between U and TU, there's one that is bigger and one that is smaller. Okay? And the question is just which way the arrow points, and that just depends on the length. So this is equivalent to saying that the length of W naught is less than the length of W naught. And something that I haven't said explicitly, and I want to say it very explicitly now. Between U and TU, there's always a relation. Either this one is bigger or this one is bigger. Between any two things that differ by a transposition, by a reflection, U and TU. And you just have to see which one the longer one is, and that's the bigger one of the two. That's exactly what I'm saying here. Okay. Now we know that the length of something W naught is the length of W naught minus the length of this thing. So this is equivalent to saying this. Right? This is L of W naught minus this. This is L of W naught minus this. And then, again, between W and TW, there is one that is bigger than the other one. And because this one has longer length, that means that bigger. And this precisely means that T doesn't make W shorter. So this just follows very easily from the definitions. There isn't really anything clever going on here. Okay. So that's the proof of my third property. And now from my third property, the fourth one follows very easily. The reason being that the length of W naught is equal to the number of elements of TLW naught. But if I plug in the identity here, I get that this is T minus TL of the identity. Okay. And I know that there are no reflections that make the identity shorter. That means this set is empty, which means this is easy. So you see the key property is number 2, which we proved last time, and everything else follows for free. Now let me show you a corollary of this. The corollary is that U is less than V if and only if U W naught is bigger than V W naught. And this is exactly what I was telling you last time, that when you multiply by W naught, then exactly what you're doing is reversing the order of the poset. So the things that are smaller than something else now become bigger than. And again, this is very easy, given the work that we've done so far, because instead of proving that the Bruhat order is reversed, let's prove that the graph is reversed, the Bruhat graph. And if I prove that the Bruhat graph is reversed, then I know the order will be. So in the Bruhat graph, I have an arrow from U to TU. If and only if this one is bigger than this one. So this means that L of TU is bigger than L of U. Okay. Now, this is equivalent to saying that L of, if I multiply by W naught, that reverses the length. So it's equivalent to saying this. Right? Because this is L of W naught minus this, and this is L of W naught minus this. And then this is exactly saying that I have an arrow from U W naught to T U W naught, but this is pointing from the smaller one to the bigger one. had an arrow from U to TU in the Bruhat graph, I have an arrow from TUW naught to UW naught in the Bruhat graph. And this tells me that multiplying by W naught precisely reverses the arrows of the graph, and I get my corollary. Okay. Any questions about that? So this is a really nice fact. It says that if you take the function that takes the function that takes u and sends it to uw naught, that this is a function that precisely reverses the order of the poset, which is what's called a poset anti-isomorphism, anti-automorphism. Multiplying by W naught, this reverses the order of the poset. This is what the corollary is saying. Now, you can imagine that if this is true on the right, this is also true on the left. And the proof goes exactly in the same way. This is also a poset anti-automorphism. And that also means that if you consider the map from W to W, where you multiply by W naught on the left and by W naught on the right, then multiplying on the right reverses the poset, multiplying on the left reverses it again. And so what you get is a poset automorphism. Okay? Now, remember that W naught is equal to W naught inverse, and so this map is exactly the map that conjugates by W naught. This is conjugation. Now, again, this raises a nice question. And the nice question that this raises is that we understand for the symmetric group what W naught is, right? W naught is the permutation that just reverses the order of everything. The W naught is the permutation n minus 1 and minus 2 up to 1. Okay. Now, what we have here then is three maps that take the Bruhat order on permutations, and two of them reverse it, and one of them keeps it the same. And so a nice question that you should take the time to figure out is what do these maps do in the symmetric group? Okay. These maps take a permutation and send it to another permutation. There's three rules for doing that, and you should understand for each one of these guys what is it that you're doing to the permutation that reverses the order in the poset.
So if I conjugate by the maximal element, then I get an automorphism. If I conjugate by the minimal element, I also get an automorphism. So what happens if I conjugate just by some element in between? Do I switch just a... Does anything like
That's weird as a question. Then. I like that question. What does the map that takes U and sends it to some W, U, W inverse do to the poset? Can you say anything nice? So for W naught, it's an automorphism. For the identity, it's just the identity. And so can you say something nice about this in general? I like that question. I don't know the answer right away, but we should think about it and talk about it in the forum. Okay. Any questions about the longest element? this is basically all I want to say about it, that it has the very nice property that when you multiply by it, it flips the poset. Now you should see that this is a very nice property that you might want to keep in mind. The length of W naught is exactly the height of the poset, right? Because it's the highest height that you see in the poset. And so what this tells you is that the poset has exactly a number of floors equal to the number of reflections. It's nice to know. Okay. Okay.
Can I make one small request, Federico?
Yeah?
When you're stating something that has lots of U's and V's and W's and things, can you just state it a little bit slower?
Okay. Sounds good. I think the request is to state the statements that have a lot of little symbols in them. I should say them slowly, and I think the Colombian students will appreciate this because the camera is a little blurry sometimes. So if I don't, then please stop me, and I will gladly do that. Okay, so that's all that I wanted to say about the longest element of a Coxeter group. And now we're going to switch to a completely new topic. And this is the topic of parabolic subgroups. It's a big word, but you'll see that it's not a difficult concept. So this is our next topic. Now, the thing is this. Here we have a very nice family of groups, Coxeter groups, and now we would like to understand what their subgroups look like. Okay? But let me tell you right away that that's a hopeless question. I mean, why is it a hopeless question? Because what does a general... I mean, let's say that we want to study subgroups of Coxeter groups. How nice are they, for example? Are they Coxeter groups? Are they... What can I say about them? Well, if I wanted to teach a class about subgroups of Coxeter groups, it would be called Math 335. Or I don't know what it's called in Los Andes. The point is, any group is a subgroup of a Coxeter group. Any finite group, let's say. Why? Because remember that the symmetric group is a Coxeter group, and every group is a subgroup of the symmetric group. And so that means that really this is just not a reasonable question to ask. I mean, these are basically all fine. Let's say, let me put it this way. All finite groups are subgroups of Coxeter groups because in particular they're subgroups of symmetric groups. This is Cayley's theorem. And so that means that this is, I mean, this question is interesting, but it's the question of group theory. This raises another question, by the way. There's a lot of questions for the forum today. What about infinite groups? Are infinite groups subgroups of Coxeter groups? Well, any infinite group is a subgroup of an infinite symmetric group, but we haven't talked about whether infinite symmetric groups are Coxeter groups. And so let's put this as another question. Are infinite symmetric groups Coxeter groups? Okay. So that I can maybe eliminate this adjective finite here. We'll talk about that. But the point is that this is not a good question to ask. And so we're going to restrict our attention to subgroups that are called parabolic. And that's a nice family that behaves very well. So we restrict to parabolic subgroups. Which are much better behaved. if you're a little bit worried that everybody has heard the word parabolic except for you, that's not true. The word parabolic subgroups is specific to Coxeter group theory, and there's no reason that you should have heard it before. So what is a parabolic subgroup? You start with a Coxeter system. Okay. And what I'm going to do is choose some of the generators. Let's call it J, a subset of the generators. Then a parabolic subgroup is one obtained in this way as the subgroup generated by J. Okay. So Wj is the subgroup generated by J. And these things are called the parabolic subgroups. Parabolic subgroups of W. Okay. So for example, we know right away how many parabolic subgroups I can build. They correspond to the subsets. So there's 2 to the S of them. 2 to the S of them. Maybe, because it could be that some of them are equal. Okay. It could be that by taking different subsets of the generators, I can obtain the same parabolic subgroup. But we will show that that's not the case. That really, these guys are all distinct. So for each distinct subset of S, there's a distinct parabolic subgroup of W. I was going to start proving some things, but maybe before I start proving some things, let's do an example. Let's do this example. Okay, and let's say that J equals these 3 guys. Then W is the symmetric group S6. Okay. And what is Wj? It's the subgroup of S6 generated by reflections S1, S2, and S3. So what is that? Basically, I am living in S6, so I have permutations of a set of 6 elements, but I'm never allowed to use the operations S4 and S5. Yeah? I'm only allowed to change the first 2, S1, S2, and S3. Okay? And so what that means is that basically I'm going to be shuffling the numbers 1 through 4, but I'm going to leave 5 alone and 6 alone. Okay? So as I said, these are the permutations of S6, the permutations of 1 up to 6, which leave 5 and 6 fixed. And these form a group. Okay. This group, of course, is isomorphic to the symmetric group is 4. Okay. By just forgetting cards 5 and 6. So this is an example of a parabolic subgroup. They're not very mysterious. They're really fairly simple objects.
Is it better to have lots of them to study or fewer
So is your question whether I want lots of subgroups or whether I want lots of elements in J?
My question is, so if we have different sets of generators, and we can have these cardinalities be different, is it better to have...
Oh, I see. If I change S. So the question is, if I fix W and I change S, because I know that I might have different sets of Coxeter generators. I mean, by changing S, what you just get is a different family of parabolic subgroups. And you know, if your interest is to study the group W by studying the parabolic subgroups that live inside there, then the more collections S of generators that you can find, the better. Yeah.
So if you have one generating set and it's smaller than another, does that mean then that its parabolic subgroups are a subset of the bigger one?
So let's talk about this example more concretely. So you saw in homework 1 that the dihedral group D6 had two different presentations as Coxeter groups. Now, one had 2 generators, one had 3 generators. So that means that according to the first one, you're going to have 4 parabolic subgroups. According to the second one, you're going to have 8 parabolic subgroups. And John's question is whether these 4 are contained in these 8. And my answer is I doubt it. You'd have to check, but I think if it would be a coincidence if that happened. But in general, you're just going to have different parabolic subgroups. And
so then this shouldn't say of W, but of the system WS.
Sure. Yeah, as I warned you you'll see all over the book, all over the papers, everything. People are always a little bit lax, and they might write W when they mean W, comma S, and in this case, really, I mean W, comma S, because a different set of generators S is going to give me different parabolic subgroups. Okay. So, well, here's a nice property of this parabolic subgroup. It's actually a Coxeter group, okay, which we know doesn't happen in general. And so this is the first thing that I would like to show, is that this is not a coincidence. So some properties of parabolic subgroups. One of them is that they're actually Coxeter groups. Okay. And you can imagine what the Coxeter system is. We already have a set of generators that comes naturally. So this is a Coxeter system. And the second thing that I would like to prove is that this is a Coxeter system, so it has a length function, which we're going to call L sub j. What I'm going to show is that the length function of the parabolic subgroup coincides with the one of W. Okay. This L sub j is the length function of Wj. Okay. So these are two very important properties of a parabolic subgroup Wj. Now, if you're taking notes, you should leave space for a 3, a 4, and a 5, which I won't state just yet. Before I state them, I want to prove 1 and 2. Now let me ask you, does 1 sound like an easy statement to prove or a hard statement to prove? You see, in the first homework, you dreaded statements like this. Right? You dreaded a statement that said something is a Coxeter group. That used to be very hard to prove. But now we have a very useful tool that is going to make this very easy, which is that we just know you can just check the exchange property, the deletion property, and we'll be done. And that's exactly what I'm going to do. Actually, I should do 2 first, and you'll see why. Well, why? Because I want to prove one using either exchange or deletion, but those make reference to the length function. And so I should understand the length function first so that I can then go over there. So Lj of W, what is that? Well, let's take our word W equals J1 up to Js. Okay? Then what? And let's say that this is reduced in Wj. Then what can I say? I can say that immediately this is a word of length s in W. And that means that the length of W is at most s. Okay? So here s is the length in Wj. Okay? How can I show that it's not smaller? So let's suppose that the length of W is smaller than s. What that means is that here I have a word for W that is not reduced. And so I can reduce it by eliminating. Okay? I can find a subword of this which is reduced. So I find a reduced subword W equals J something, J something, J something, where this is less than S. But these are all in J. These are all in Wj. And this means that this is also a word for W in the Coxeter group, Wj, which contradicts that this one was the shortest one. So all in J, and so this is a contradiction. Okay. Question?
Yeah, didn't you just use the fact that it's a Coxeter group, and now you're going to use this to prove the first one? Is that what you said?
That's a good point. So I used this. I said I can find a reduced subword, and I'm not sure exactly how I said it, but if you remember when we were proving these things, we ran into the same problem, and I told you that if you look carefully at the proof, we never really used Coxeterness. We just used what I used here. In fact, let me prove. No, hold on. The thing is that what I said here is W is a word in W. And W is a Coxeter group. And I can reduce it because I know that W is a Coxeter group. I don't know that about Wj yet. So here I'm using that W is Coxeter. I didn't use that Wj is Coxeter. Okay. And now, basically, I want to make exactly the same argument, but in the first one. Okay. So now, to check that it's a Coxeter system, I just need to check, for example, the deletion property or the exchange property. Either way, let's say the deletion. Well, so first of all, what's the point? The point is that Wj is generated by J, where these guys all have order 2. And this is the first condition of Matsumoto's condition that says that now I just have to check deletion. Okay? So I check deletion. Suppose that I write W as J1 up to Js, and suppose that the length of W is not S. It's smaller. Okay? Well, I know that the length sub j of w is equal to the length of w. And so here I have, again, a word for w in the generators which is too long. And so now I use deletion in w. So I use deletion in w to say that I can rewrite w as j1, then I remove one of these guys, remove some other one of these guys, and js. And there's deletion. Yeah? I took a word that was too long in wj, and I found a shorter one obtained by deleting two guys. So the point is that wj inherits from w the deletion property for free, and I have absolutely nothing to say here. As long as the length functions are the same, which is why I needed to check that. Okay. So these things just come for free. Okay. There's really nothing to prove about these two statements.
These are exactly the subgroups that have this property. That inherit this little.
Yeah. Yeah. So these are two properties about individual parabolic subgroups. And what I would like to do now is explain to you how different parabolic subgroups relate to each other. For example, we know that if you have a group and you have two subgroups of it, then when you intersect them, you get another subgroup. So what happens when we intersect two parabolic subgroups? We get some subgroup, and we hope that it's parabolic. And it turns out that it is parabolic, generated by the intersection of I and j, okay, which is what you would expect. Now, in a group, if you take two subgroups and you take their union, then that is not necessarily a subgroup. And to make a subgroup out of it, you have to take the subgroup generated by it. Okay? And so you might ask, what happens when you do that with parabolic subgroups? Hopefully, we get a parabolic subgroup back, and we do. What we get is exactly the parabolic subgroup for the union. Okay? So that's also very nice. And the last property is, I just want to say that different sets of generators give rise to different parabolic subgroups. So if two parabolic subgroups are the same, it's because really they're not two. They're the same one. Okay? So these are three nice properties that explain how the different parabolic subgroups relate. Okay? And this is one of the homework problems. Just to check these things. Okay?
So in the Bruhat graph, I can think of this as just some little lattice sitting inside of my big lattice.
Yeah, why don't we talk about that actually? So we talked a little bit about posets last time. And here's an example that I didn't talk about last time. Let's say that you have some group, and you consider the set of subgroups. Okay? Let's call it, I don't know, S. Subgroups H of G. I can make a poset out of these by saying that H is less than I if H is a subgroup of I. It's the only natural poset that you make. So make a poset by saying that H1 is less than H2 if it's a subgroup. Well, if H1 is a subgroup of H2. So this is a nice poset, the poset of subgroups of a group. And in fact, this is a very nice poset. So let me tell you a little bit about this poset. There's a very nice family of posets called lattices. Okay? So a poset is a lattice. If every two elements of the poset, they have exactly one unique lowest upper bound. You mind closing the door? Thanks. Two elements of the poset have a least upper bound, which we denote by this, x wedge y, and a greatest lower bound. Which we denote by this thing. Okay? So that's what a lattice is. Okay? So you can imagine that if what the lattices look like, well, basically you have some poset here, and if you want to know what are the things that are bigger than x and y, then there's going to be a unique one which is smallest and bigger than them. And then the things that are bigger than x and y are exactly the things that are bigger than this guy. Okay. So these are the things that are greater than or equal to x and greater than or equal to y. And the same down here. This is the greatest thing that is less than them. And if you want to know what's less than x and y, then it's basically everything under this guy. Okay. So for example, is the Bruhat order a lattice? This is what lattices look like. So is the Bruhat order a lattice in general? Well, let's test that with the smallest example that we know. The Bruhat order of S3. It looks like this. We have the bottom element E. Then we have S1, S2. Then we have S1, S2. We have S2, S1. And then we have S1, S2, S1, which is the same as S2, S1, S2. And I'm asking you, is this a lattice? And you see that it's not a lattice because, for example, these two guys don't have a least upper bound. Because these two guys are minimal upper bounds. Okay? So this is not a lattice. Now, what is it that we're saying then? We are saying that, for example, let's talk about the lattice of subgroups of the symmetric group S4. Okay? So don't worry, I'm not going to draw this. I would never finish. But what is the biggest subgroup of S4? Itself, right? That's the biggest. What's the smallest? It's the identity. Okay. And then there's a bunch of subgroups in between, which are ordered in some way that just get kind of a mess of a poset. I have no idea how many things are in there, but I know it's a lattice. What I do know is that now there's certain subgroups that I like that live in there. The parabolic ones. Okay. What are the parabolic ones? Well, S4 looks like this. How many parabolic subgroups do I have? Let's call this S1, S2, S3. That means that I have 8 parabolic subgroups, and they all live in here. Okay. And those are actually, so they live in here somewhere, and they're going to look like this. This bottom guy is a parabolic subgroup, right? It's the one generated by the empty set. And this guy is parabolic, it's generated by everything. And then I have the one generated by S1, so W sub S1, W sub S2, W sub S3, and here's W sub S1, S2, W sub S1, S3, W sub S2, S3, and W sub everything. And this is one of our favorite posets. Because what am I saying? When is something a subgroup of something else here? Well, you can easily deduce from what I'm saying over there that it's precisely when there's a containment of generators. Okay. So I have these relations, that each one of these guys is a subgroup of the other ones. And so what I get is a cube inside this thing. Now, don't be misled. There's a lot of other things here. Yeah? There's a lot of other subgroups here. And so this lattice of subgroups might be very complicated, but I have a very nice sublattice, which is the sublattice of parabolic subgroups, and that's just a cube. So what I drew here is the sublattice of parabolic subgroups. And this is isomorphic to what's called the Boolean lattice, and what it is just the hypercube. Boolean lattice, which is the lattice of subsets of S1, S2, S3. Okay. It's kind of a long answer to your question, but it's a nice answer, I think. It means that there's really, for any group, there's a very nice structure. There's a lattice of subgroups, and when you're talking about a Coxeter group, then this might be a pretty complicated structure. For example, we know that if you put a symmetric group here, then eventually you're going to see any group in this lattice for n large enough. Okay. So these things can be pretty complicated, but they have a very nice structure inside, which is the structure of parabolic subgroups. Okay. And that also tells you that parabolic subgroups are just much nicer and much better behaved than general subgroups. Okay. All right, any questions? Okay.
But it would seem that in some respects, the lattice is almost uninteresting because so many of the groups are isomorphic to each other.
I'm sorry?
It would seem that in these lattices, for even bigger and bigger groups, most of these subgroups are going to be isomorphic to each other.
It's a
all
good
the
point.
ones on
For
that
example,
first
these,
tier.
these three are isomorphic.
Right, and then two of the ones on the second tier. Yeah. So I'm not sure what that gives us, but it seems like the whole idea behind this is kind of reduced in some regards.
So, right, so you might ask yourself, for example, and you can make a different structure, which is the subgroups where you identify two if they're equal, if they're isomorphic.
Right.
And there would be kind of a substructure of this, which would be more complicated, actually. I mean, in some ways, you, for example, in this, one of the homework problems is to understand all the parabolic subgroups of this matrix. So you guys will do that.
Of what? Of SM?
Yeah. But in some ways, you already know what the answer is going to be. Is that they're going to form a nice hypercube like this, and so they're going to be a fairly nice structure. Now, if you kind of collapse them by saying, let me look at them, but let me identify two of them if they're different but isomorphic. It won't be linear actually. Actually, maybe I'll add that to the homework. It's your fault.
What? So it is.
Because.
Yeah.
I mean, for example, if I say, let me draw the same picture, except now I want to identify groups that are isomorphic. So what does it look like? Well, basically, these three guys are isomorphic, so they're going to be identified. Now here, these two are isomorphic, but this one is not. Because they have, I mean, the diagram for this one is 2 and 3. The diagram for this one is 1 and 2. The diagram for this one is 1 and 3, and they're not the same. So they're different. That means that here you're going to have two different kinds. And then a top one. And I might ask you to explain this in general. This is nice.
Interesting. Yeah, I guess it is a sublattice in that.
So it is
If you look up straight from.
I'm not sure if in general it's a sublattice, but there's something. I mean, there's basically a Poset map, which I think this is not a sublattice, but something called a quotient of a Poset, whatever that means. But the point is that you can also understand this, and it's another nice structure.
So
Actually, that's also something that you guys should play with, and if you get into it, this could also be a good start of a project. I'm not
Quotients of Poset map.
but even just this one, I mean, just studying the Poset of